to this course on gas turbines and jet engines. So, today is lecture number 8. So, this is the third lecture of week 2 and today we are going to study combined regenerative reheat gas turbine, or for ideal case combined regenerative reheat Brayton cycle, okay, which is the ideal gas turbine cycle. So, the concepts that are going to be covered in this course are concept of combined regeneration and reheating, how it is applied to a Brayton cycle, and analysis of combined regeneration reheat cycle, and we will also do some numerical calculations. So, let us start by drawing the TS diagram of this regeneration reheat combined regeneration reheat cycle. Of course, you should be able to combine the component diagrams also for the regeneration cycle and the reheat cycle to get this combined cycle component diagram. I leave it up to you as an exercise. We will go ahead with the TS diagram. Okay. So, similar to the previous cases, we have compression from 1 to 2, then expansion constant pressure heat addition, which is the combustion process going from 2 to 3 like all the other cycles. Then the first expansion occurs in the high pressure turbine going from 3 to 4, let us say. Then again heating, which we have seen is called as reheating at the reheat pressure to go to 5. Remember that temperature at 5 is equal to temperature at 3, because that is the maximum temperature that can be sustained by the turbine blade. Then the expansion in the second turbine, which is the low pressure turbine going from 5 to 6. Okay. This is similar to the reheat cycle. Let us erase this. Okay. And then in reheat cycle we would close the cycle going from 6 to 1, but here we have two additional processes. So, we have, let us draw in another color, we have the regeneration processes. So, going from 2 to say 7 for ideal case with optimal design parameters, this T 7 is equal to T 4 equal to T 6. So, going from 2 to 7 is the heat transfer to the air in the regenerator, okay. And the corresponding process where heat is extracted from the combustion products goes from 6 to 8. Okay. For again for 100% regenerator effectiveness, T 8 should be equal to T 2. So, this is the complete cycle. So, in real case, if I have a combined regeneration reheat gas turbine, the exhaust gases will go outside to the atmosphere at state 8, but in the ideal cycle we close out the cycle, so that we can have a cyclic process by adding this constant pressure heat removal 8 to 1, okay, as we have done for all the other cases. So, this is the complete cycle. So, the two heat addition processes are from 7 to 3 and from 4 to 5, which should be equal for the optimal case. Okay, let us try to analyze this cycle. So, for optimum work output, for optimum condition or optimum condition, okay, we know that T 4 should be equal to T 6 and T 7 also should be equal to T 4, okay, or T 6. T 7 should be equal to T 6 because we are taking epsilon to be equal to, so the effectiveness to be equal to 1. Let us write this again. So, this is equal to 1. Okay. So, similarly, for this case T 8 also should be equal to T 2, and we also know that in general T 3 is equal to T 5, because this is the maximum temperature, which is also known as turbine inlet temperature, maximum temperature sustained by the turbine. So, it is a design parameter known as turbine inlet temperature. So, now the analysis is similar to all the previous cases. So, in this case the net work output, we start with the net specific work output. This has two components, as we know already. One is the high pressure turbine expansion, another is the low pressure turbine expansion, and then we have to subtract the compressor work, okay, the work required for running the compressor. So, C p T 3 minus T 4 minus plus C p T 5 minus T 6 minus C p T 2 minus T 1. So, this is the net work output, and this is similar to the case for with only reheat, okay, because here regeneration does not change the work output from the turbine, neither does it change the work input to the compressor. So, the net work output remains same, okay, same as reheat cycle. Same as reheat cycle. What about the efficiency? So, efficiency will also depend on the net heat addition, and the heat addition decreases because of the regeneration, which we want, of course. So, the heat addition is now, there are two heat additions, one is the primary combustion going from 7 to 3. So, the heat addition is T C p T 3 minus T 7, let us write it again clearly, T 3 minus T 7 plus the secondary combustion or the reheat process, where the heat addition is equal to C p T 5 minus T 4, okay. Sorry, T 5 minus T 4, correct. So, now if 4 and 7 are equal and T 3 and T 5 are equal, then both of these heat additions, this is equal to this, okay, and we can write this as 2 times of any of these heat additions. Okay. Now, if we try to find the efficiency is W net, we already know by the heat addition, okay, the combined heat addition in this case. So, what is the W net value? We have already seen that is equal to. So, we will write in terms of slightly modified form, where we take out T 1. So, that we have T 3 by T 1 minus T 4 by T 1, similarly plus T 5 by T 1 minus T 6 by T 1 minus T 2 by T 1 plus 1. Okay. So, this I will directly write down. It will come of this form 2 T minus C and plus 1 minus 2 T by root C, not 6. Two T minus C plus 1 minus 2 T by root C. So, this is the net work output, this divided by heat addition, which also we can write in the similar way, C p T 1, and the heat addition was equal to. So, if I take T 1 common, then T 3 minus by T 1 minus T 7 by T 1, T 5 by T 1 minus T 4 by T 1. Okay. So, you can also try to derive on your own parallelly. So, this will be equal to, so this is T minus T by root C plus T minus T by root C. Okay. From the previous slide we have seen that. So, T 3 by T 1 is T and T 7 by T 1 is T by root C. Okay. Same case again. So, C P T 1 gets cancelled and we are left with. So, after some cancellations you will get an expression of this form 1 minus C minus 1 by 2 T minus T by root C. Okay. Again I would like to emphasize that this is not a formula. So, you should not be used as a formula. This is a derivation which we have done, so that we can plot the performance characteristic efficiency for different values of pressure ratio and so basically different values of C and temperature ratio T. So, that we can generate the performance maps. Okay. So, this is the efficiency. So, if once we solve a numerical problem, it will be clear whether the efficiency increases as compared to a simple regenerative cycle or it decreases, or of course, we expect that the efficiency will be higher than that of simple reheat cycle. Okay. We will compare all this by solving a problem, numerical problem next. Before that, let us qualitatively try to understand the performance characteristics for this case. So, the net work output or the non-dimensional net work output versus R profiles remain exactly same as the case with reheat, because there is no change in the net work output. So, the only variation that is of interest to us in this case, so we will read out this line, because try to redraw in a more straight way. Okay. So, although it is not good, we will manage with this. So, the only performance characteristic which we expect to change is efficiency versus R, and if we draw qualitatively all the different cases and compare, for simple Brayton cycle we know that the efficiency goes like this. Okay. This is standard Brayton or simple Brayton. I will write simple or standard. Keeps on increasing, and we know that for regenerative cycle, let us draw using another color. For regenerative cycle, the characteristics is opposite. So, the efficiency decreases and at some point it goes below that of the simple Brayton cycle. Okay. So, this is for regeneration, and we have seen what should be the crossover point for this case, which is the compressor outlet temperature is equal to the turbine exhaust temperature. Anyway, let us say that this is equal to T equal to 5, T equal to 4 and T equal to 3. We know that efficiency for simple Brayton cycle does not depend on the temperature ratio, but for all the other cycles, like for this case for the regeneration cycle, it increases with temperature ratio and decreases with the pressure ratio. Now, for reheat also we had drawn, and for reheat cycle we got something like this. So, it is lower than that compared to that of the standard cycle, but is a function of temperature or temperature ratio. So, with increasing temperature ratio we approach the standard cycle efficiency, but can never reach the actual value. So, this is for reheat. So, finally, coming to reheat plus regeneration. So, the behavior is qualitatively it is similar to that of regeneration cycle. Okay. Whenever there is regeneration, the behavior becomes like that. So, with reheat and regeneration, however, although adding only reheat to a simple cycle decreases the efficiency, adding reheat to a regenerative cycle increases the efficiency. So, the efficiency is the highest among all these 4 cycles and will be something like this. Okay. So, what is the value at C equal to 1 or R equal to 1? It goes to 1, okay. C equal to 1 and then T, if let us say T is equal to 5. Okay. So, there is some numerator value, denominator value, numerator is 1. So, it will be something like this. The crossover also occurs much later. Okay. So, this will be T equal to 5, although the diagram has become complicated, T equal to 4 and T equal to 3. With increasing temperature ratio, the efficiency increases, but for any temperature ratio, the efficiency is higher as compared to the regenerative cycle where there is no reheat. Okay. This is in contrast to the case where if it is a simple Brayton cycle, adding reheat is decreasing the efficiency, but here it is increasing the efficiency. What is the reason for that? Think about the reason for that, because why we are getting contradictory behavior. Okay. And you can find what are the crossover points. Okay, crossover for, let us say, for this reheating cases, this not this will be the crossover. Similarly, this will be a crossover point and this will be the crossover. Okay. So, we will try to see what sort of values we get when we solve a numerical problem based on the same framework that we have used so far for all the other cases. So, that we can have a direct comparison of the results. Okay. And with that we will end this class. So, exercise problem is taken as exactly similar to the cases studied till now. I will start by drawing the TS diagram, okay, and then define the problem, because anyway TS diagram needs to be drawn. Sorry. So, T and S, okay. So, I will quickly draw the TS diagram. So, these are all the processes going from 1 to 2 compression, then 2 to 7 is the regeneration in the air side, then 7 to 3 is the first conversion process, okay. Then 3 to 4 is the first expansion or high pressure turbine expansion, 4 to 5 is the second heat addition or conversion process, then 5 to 6 is the expansion in the second turbine or low pressure turbine, then 6 to 8 is the heat removal in the regenerator from the conversion product, and we close out the cycle by using this 8 to 1 constant pressure heat removal. Okay. So, if we use something else, so this is the regeneration part and going from here to here, this is the regeneration, and reheat part already you know that this is the reheat part. So, both are present. So, now let us define the problem. So, problem is taken as exactly similar problem, T 1 equal to 300 Kelvin. At this point I suggest that you can pause the video and go back to the previous class to see what were the values that we are obtaining for the same problem, where we had separate cases of regeneration, separate cases of reheat, and the simple Brayton cycle. Okay. So, T 1 is 300 Kelvin, pressure anyway is not needed, if needed you can assume it to be 1 atmospheric pressure. Then overall pressure ratio we had taken as 10, temperature ratio was 5, this is based on the value that T max is equal to 1500 or turbine inlet temperature is 1500 Kelvin. So, from that we obtain T equal to 5. Okay. These were the conditions, and we had assumed that air has standard Cp value of 1.005 kilojoule per kg Kelvin and gamma is equal to 1.4. Okay. Now, the additional constants that we are going to pose are that similar to the reheat cycle here, the reheating occurs at optimum pressure. So, reheat at optimum pressure, exactly same as the previous problem, and regenerator effectiveness is 100%, that is also similar to the previous problem for regenerator. Okay. So, now we want to find out ultimately, let us write here what is the efficiency and what is the net specific work output. So, every time we are determining these parameters, why? Because these are the indicators of the performance of the cycle, these are the performance characteristics, and the parameters that we have written, these are the design parameters or the parameters which are fixed while designing the system, gas turbine system. So, pressure ratio and turbine inlet temperature are the two main design parameters. Of course, the fluid also is fixed, standard fluid will be air. Okay. So, now because most of the calculation is similar to the previous cases, I will just quickly write down the values and you can note from the previous example. We already know what is the value of T 1, T 1 is 300 Kelvin. From the compressor pressure ratio, we will get what is the value of T 2, it will be exactly same as all the previous cases. So, I am directly writing down, you can try to calculate again for practice. 579.21 Kelvin, T 3 is known to us. So, I am writing down all the temperatures at each state following our methodology of going step by step instead of trying to use the derived expressions. Okay. Then using the relation for T 3 to T 4 expansion in the turbine, which should be equal to the pressure ratio is equal to root of R. Okay, that also we know, we have seen for the reheat cycle. So, the T 4 will be same as that we had obtained in reheat cycle. Okay. Actually, all the temperature values are known to us from previous calculation, but the definition of efficiency is different in this case, not the definition, but the expression for efficiency. T 5 of course, is 1500 Kelvin, assuming that both T 3 and T 5 are at same temperature, because that is the turbine inlet temperature, maximum temperature. T 6 can be obtained similar to T 4, T 6 is equal to 1079.53 Kelvin. T 7 is equal to T 6, okay. T 7, because this is ideal regenerator, T 7 equal to T 4 equal to T 6. Okay. So, this is equal to T 6, which is 1079.53 Kelvin, you can note down, and T 8 is equal to T 2, which also we know, this is equal to 579.21 Kelvin. Let us write this down also, because we have written all the other values. So, now the net work output, which we know should be equal to, so this first work output plus the second work output minus the compressor input. So, Cp T3 minus T4 plus Cp T5 minus T6 minus Cp T2 minus T1. This is same as the reheat cycle, because there is not going to be any change by adding regeneration to the work output, there is no change. So, this is equal to 564.54 kilojoule per kg. The efficiency on the other hand is equal to W net by net heat input. In this case, the net heat input is 2 into Cp, because both the heat inputs are equal. I will write in terms of one of them T3 minus T7, or you can write Cp T3 minus T7 plus T5 minus T4. Okay. So, we know all the values of the temperature. So, this comes out to be 0.668, okay, or 66.8%. So, the net work output does not change, but the efficiency, if we compare to the previous cases, is highest as compared to all the previous cases. Okay. So, if I want to summarize, so this is how we should solve all these problems related to Brayton cycle and these modified Brayton cycles. Okay. All these are useful, all these modifications for industrial gas turbine. We will later see under what conditions those are applicable, under what are the advantages, disadvantages. Okay. So, based on our calculations, if I want to compare the results for standard cycle, regeneration cycle, reheat cycle and combined regeneration and reheat cycle, we have found that for the given condition, temperature is 300 Kelvin at the inlet, pressure ratio R is 10 and temperature at the turbine inlet is 1500 Kelvin. For standard and regeneration cycle, the work output is 446.08, as we expect, both will be equal, and for reheat and regeneration plus reheat, significantly higher value is obtained, which is 564.54. The efficiency for the standard cycle is 48.2%, whereas if I add regeneration, we get up to a high value 61.4%. Remember, all these are ideal cases. In real cases, efficiency will be significantly lower. We will also solve problems for real cases later on in the course. Then by adding reheat to the simple cycle, the efficiency gets lowered quite significantly, we go to 41.9%. On the other hand, in contrast, if I add reheat to the regeneration cycle, then the efficiency actually increases and we go to a value of 66.8%, the highest efficiency is obtained. So, we see that with regeneration and reheat we get the highest work output as well as the highest efficiency. Okay. Why this efficiency is highest in this case and why this behavior is different as compared to simple reheat cycle? Because adding reheat, if you think of it, adding reheat increases the exhaust temperature, the turbine exhaust temperature. So, we have a larger temperature difference for regeneration. So, reheat plus regeneration is very effective, because now we have more scope for regeneration. So, which increases the efficiency. Okay. So, with this we have reached the end of this class. So, we to conclude or to summarize, ও তাহলে আমি আবার হ্যাঁ এটা হঠাৎ খুলে পড়ে গেল কেন? আচ্ছা, টাইট করার কিছু আছে? এটা বোঝানো হয়ে গেছিল। আচ্ছা, আমি আবার এই স্লাইডটা থেকেই শুরু করছি। হ্যাঁ, তাহলে আমি এই দাগগুলো একটু ইয়ে করে দিই। Huh. Well, so, now if we compare the numerical values for the all 4 cases, the standard cycle, the regeneration cycle, the reheat cycle and the regeneration plus reheat cycle, the values which are obtained based on our problem. So, the design parameters were R equal to 10 and the turbine inlet temperature was equal to 1500 Kelvin and with ambient temperature 300 Kelvin. So, turbine so the temperature ratio was 5. Okay. We see that as expected the net work output for the standard and regeneration cases are equal to 446.08 kilojoule per kg, whereas for reheat cycle and regenerative plus reheat cycle it is significantly higher. The numerical value is 564.54. Okay. So, more than 25% higher. For efficiency, the standard cycle has efficiency of 48.2%, which increases considerably to a value of 61.4% when we add regeneration to the standard cycle. However, adding reheat to the standard cycle decreases the efficiency quite considerably and we go to a relatively lower efficiency of 41.9%. But adding reheat to regeneration behaves in an opposite manner. So, in this case adding reheat to the regeneration based regeneration cycle increases the efficiency and we reach a efficiency, a very high efficiency of 66.8% based on the realistic values that we have taken for our design calculations. Remember that these efficiencies are on the higher side because we are considering ideal cases. For actual cases with losses, the efficiencies will be significantly lower. So, again just to emphasize, with reheat plus regeneration we get very high efficiency, but we also get high work output. So, this has the benefit of both high work output plus the highest efficiency among all these 4 cycles, and you should try to think and logically try to find what is the reason for which this adding the reheat to the regeneration increases the efficiency, while adding reheat to standard cycle decreases that efficiency. So, we can think of it in terms of the cycle. When reheat is added, let us use another color, the exhaust gas temperature increases. So, after adding reheat, as a result the scope for regeneration also increases. So, by adding reheat we are not only increasing the work output, but also it increases the scope for regeneration, which means that the temperature difference between T6 and T2 is higher. As a result, the regeneration is much more effective when it is combined with reheat. So, the combined cycle gives very high efficiency. So, with that we will stop today. We have seen, to briefly summarize, we have seen how to analyze combined regenerative reheat cycle, compare the values of standard Brayton regenerative reheat and regenerative reheat cycles for same design parameters, and along the way we also learned the procedure to solve numerical problems for regeneration reheat cycle problems. So, these are the references, and with this we end our class today. Thank you.